Let's explore electrophilic aromatic substitution. Now, we've already talked about electrophilic addition, but in this case, when we have an aromatic compound, we're more likely to substitute for one of the hydrogens on the aromatic compound. And the reason for that is that we will be able to reform the aromatic ring, and that is very stable. So let's go over the general mechanism for this and talk about this reaction a little bit. So for this, we're going to start off with largely focusing on benzene rings, and then a while later we'll explore other rings that have substitution on them or different modalities here. So we'll start off with benzene and an electrophile. And we'll need a fairly strong electrophile, one that is stronger than H+. And as you know, H+ is a pretty good acid, so we'll need a fairly strong electrophile. And this first step, where we have electrophilic attack, so we have a concentration of electrons right here, and we have an electrophile right there. This initial step is our rate determining step. And that's because we're breaking the aromatic, we're breaking the aromaticity. And we're also forming a carbocation right here or right there, depending on where you draw it. In this case, since we have a symmetrical, just the benzene ring, it doesn't really matter which way we draw it. So now we have broken the aromaticity and we've generated a carbocation right here. Now, this carbocation does have resonance stability, and I'll go ahead and draw the resonance structures out for us. So if this double bond were to shift over here and be in between here, that would move the carbocation over into this para position. Like so. And we could also have this double bond shift position right over into here and put the positive charge right there, the carbocation. So it can move a little bit about the ring. Like so. So it does have some stability, and we would call these ions right here an iridium ion intermediate. This is also known as a Wieland intermediate, and that's named after an American chemist. Okay, so let's go back up to our mechanism and come back at this. So we'll need a base, and this is not going to be a particularly strong base because we're going to have an electrophile in here. And electrophiles are also acids. And so we can't have a very strong base inside of this reaction mixture for this to happen. However, we don't really need a strong base because we do want to reform this aromatic ring. And this second reaction is relatively fast. So rate determining step is breaking the aromaticity and forming a carbocation. So we've completed the electrophilic substitution, electrophilic aromatic substitution right here. Now, these reactions are generally irreversible. That is, this product right here is more stable. It's a lower energy than what we started with. And that's generally a function of the fact that we have to use fairly strong electrophiles for this to happen at all. So, since this reaction is irreversible, it will take place under kinetic control, not thermodynamic control. Now, we look at this electrophilic aromatic substitution, and we can talk about the fact that, again, this first step is slow. That means that this is the rate determining step. So the concentration of our aromatic ring and the concentration of the electrophile will be important in the rate of the reaction. Generally speaking, most of the time we're generating our electrophile in situ. A lot of these electrophiles are very reactive, and so we'll generate those as we go along, often catalytically. But it is important to consider the reaction kinetics, that we have the aromatic ring, of course, is part of that rate determining step, but also the electrophile. And so the concentration of these two species will drive the rate of the reaction.